Good morning. Today we'll be learning about the linear transformation of multiple mental information, particularly the line Weber. I'll share the slides now. Okay, so we'll be seeing about the line Weber transformation today. Okay, so multiple mental enzyme kinetics, when you know the enzyme kinetics and the highly specific catalysts and all these things you are very familiar with the thing. So I'm quickly understand that our matrix mental equation, I'm not going to need the derivation of this matrix mental equation and all. I'm starting from the matrix mental equation as such, the denote is equal to V max into substrate concentration upon Kn plus substrate concentration. So we will see now that there are three most linear transformations of the matrix mental equations, and they are the line Weber or the double reciprocal transformation. The second one is the epoxy transformation, and the third one is the Phillips-Wurth transformation. Today we will be learning about line Weber for the double reciprocal transformation. So this equation is obtained by taking the reciprocal on both the sides of the matrix mental equation. The double reciprocal, also known as the LB plot or the line Weber plot, is created by plotting the inverse initial velocity, that is 1 by V naught, as a function of the inverse of the substrate concentration 1 by substrate concentration. The Vmax can be accurately determined, and the scale can also be determined with accuracy because a straight line is thin. The slope of the resulting line is a Km by Vmax, and y-intercept is a 1 by Vmax, and x-intercept is a 1 by K. Using the matrix mental equation, the Vmax is a asymptote and can only be the approximate and only be approximated, and as a result, the Km, which is Vmax by K, can be determined accurately. This plot is a useful way to determine different inhibitors such as competitive, uncompetitive, and non-competitive rates. So matrix mental plot we can see here. The most and the right side you can see the line Weber plot, and the most favored plot by researchers is a repeat plot, and it has two distinct advantages over the matrix mental plot. The first one is it gives a more accurate estimation of Vmax and more accurate information about inhibitions, and it increases the precision by linearizing the data. So here you can see in the left side, you can see the matrix mental plot, and when the substrate versus the velocity is being plotted, you can see the Vmax can be any of these. You cannot have it because as a plateau formation is happening, there can be errors in calculating the Km and V. Okay. So in the line Weber plot, first what we are going to do is that is we are going to invert the equation. Okay. Invert the equation on both the left-hand side and the right-hand side. Okay. So, and after doing that, we will get this 1 by V naught is equal to Km plus substrate concentration upon Vmax into substrate concentration. And when this is being done, we can see that like the when we just split it and right, like in the left hand side, you can see Km by Vmax into substrate concentration plus substrate concentration upon Vmax into substrate concentration. So here, what we can do is like the substrate concentration and the substrate concentration here get cancelled, and it becomes 1 by V naught. That's how we obtain 1 by V naught is equal to Km by Vmax into substrate concentration plus 1 by Vmax. So now we have got like this. As I told, 1 by V naught is equal to Km plus substrate concentration upon Vmax into substrate concentration. So now this is in the format where y is equal to Nx plus C, which is a linear equation. So y can be 1 by V naught is the y, Km by Vmax is the m. The substrate concentration becomes x over here, and 1 by Vmax is a c. So when we plot here, you can see that 1 by substrate concentration against 1 by V naught when I am plotting, the slope will be Km by Vmax, the y-intercept will be 1 by Vmax, and the x-intercept will be minus 1 by Km. So what the limitations are there? When substrate concentration is very large, 1 by substrate concentration, what we are plotting here becomes very small, and it becomes difficult to plot. So that is one of the negative or the limitations of the line inverter plot. So for competitive inhibitors, the inhibitor competes with the substrate molecule to bind to the binding site. Then the Km will increase without changing the Vmax value, and this means that two graphs will have the same y-intercept. You can see over here the same y-intercept. However, the new x-intercept may be quite elusive. For this type of inhibitors, a higher concentration of the substrate is needed to get half of the active sites occupied. Therefore, Km2 will be larger than it, because that is moving towards the side. So this red line is a new one. So that becomes larger than this Km1, which is a purple intercept over here. The x-intercept has a negative sign in front of it. Thus, on the graph, it has to move to the right relative to the previous intercept because it is increasing. To show this on a double reciprocal plot, the slope will increase to show the length of the binding competitive inhibitor. While the slope increases with the presence of the inhibitor, the y-intercept remains the same in presence and absence of the inhibitor. So those are the features of these competitive inhibitors and how we can represent it in the AB plot. For uncompetitive inhibitors, the inhibitor will only bind to an enzyme substrate complex. So therefore, it does not compete with the substrate for the binding site. Consequently, both Km and Vmax values decreases. Consequently, the reciprocal value of the new Vmax should be at a higher position. You can see here in the graph, the red line on the y-axis as a fraction becomes larger when the denominator gets smaller. The new reciprocal value of Km will move to the left as it has a negative sign associated. And to show this on a double reciprocal plot, the slope will remain the same as if the enzyme was not bound to the inhibitor, but the x-axis intercept will decrease. The double reciprocal plot for enzyme with and without competitive inhibitor will be just as you can see here, two parallel lines. So here what happens is like the Km is reduced and the Vmax is also reduced. Now, in the case of non-competitive inhibitors, the inhibitor can bind to the enzyme before the substrate can bind to the binding site. It does not have to wait for the enzyme to become an enzyme-substrate complex in order to bind to the enzyme. The inhibition will cause a decrease in the Vmax value while the Km is unaffected. This means the value is minus 1 by Km remains the same for the two lines, while the new value 1 by Vmax is higher relative to the previous one. To show this on a double reciprocal plot or the AB plot, the decrease in Vmax will increase a y-intercept with a larger slope. The blue lines present the reciprocal velocity with no inhibitor present, and the red line is with inhibitor. So here you can see Km is unaffected, but the Vmax is reduced. That's all for today. Thank you.